Previously we used the formula dynamic pressure equals a half rho v squared. From this we can see that dynamic pressure depends not only on the speed of the aircraft, but also on the air density, rho. This density varies with temperature and pressure and thus with altitude. The airspeed indicator is calibrated to read true airspeed for the air density of 1,225 grams per cubic meter, which would be produced by the International Standard Atmosphere mean sea level pressure of 1013.25 millibars and a temperature of plus 15 degrees Celsius in dry air conditions. No allowance is made in the calibration for the change in density which occurs with change of altitude. It follows that, even if there were no other errors, the airspeed indicator could only indicate the true airspeed when International Standard Atmosphere mean sea level air density existed at its flight level. That's to say, when the aircraft was flying in air having a density of 1,225 grams per cubic meter. This density value can only be found at or close to sea level, depending on how much the actual conditions deviate from standard. Manufacturing imperfections and usage result in small errors, which are determined on the ground under laboratory conditions by reference to a datum instrument. A correction card can be produced for the speed range of the instrument. We heard earlier that position error is alternatively known as pressure error. Position error arises mainly from the sensing of incorrect static pressure. Position errors throughout the speed range are determined by the aircraft manufacturer during the test flying program for a particular aircraft type. It's not unusual to compile a joint correction card for position and instrument errors and place it in the aircraft near the ASI conturned. To summarize then, the indicated airspeed, plus or minus instrument error correction, and position error correction equals the calibrated airspeed. Unless the air around the aircraft is at the calibration density of 1,225 grams per cubic meter, which can only occur near sea level, the airspeed indicator cannot correctly indicate true airspeed. From our formula, we know that dynamic pressure is proportional to density. So at altitude, where density is less, the dynamic pressure generated by a given true airspeed will be less than for the same true airspeed in flight at sea level. Airspeed indicator capsule expansion will be proportionately less, and the speed indicated will be less than the true speed. The difference between indicated airspeed and true airspeed is called density error. This density error will cause the airspeed indicator to underread at altitude, whereas if you get to fly below mean sea level, it will overread. Use the mouse to move the aircraft higher or lower and note the change in true airspeed. It's possible, on some navigation computers, like the CRP5, to be able to correct for density error, computing true airspeed from the calibrated airspeed which we mentioned earlier. This computation allows for the height of the aircraft above the calibration 1013.25 millibar pressure level, and also for any temperature deviation from standard conditions. Summarizing, the true airspeed equals the calibrated airspeed plus or minus the correction for density error. Some airspeed indicators incorporate colored markings on the dial. These range markings consist of colored arcs and radial lines. The white arc denotes the flap operating range, from stall at maximum all-up weight in the landing configuration, full flap, landing gear down, wings level, power off, up to VFE, maximum flaps extended speed. The green arc denotes the normal operating speed range, from stall speed at maximum all-up weight, flaps up, wings level, up to VNO, normal operating limit speed or maximum structural cruising speed, which should not be exceeded except in smooth air. Operations at indicated airspeeds in the green arc should be safe in all conditions, including turbulence. The yellow arc denotes the caution range, which extends from VNO, normal operating limit speed, up to VNE, the never exceed speed. The aircraft should be operated at indicated airspeeds in the caution range only in smooth air. A red radial line denotes VNE, the never exceed speed. If the pitot head becomes blocked, the airspeed indicator reading will, in general, remain unchanged. In level cruise, a blockage will lock in the previous pitot pressure and any change in actual airspeed will not be registered. If altitude is changed with a blocked pitot head and a clear static source, the indicated airspeed will increase during a climb because the pressure locked inside the capsule remains constant while the static pressure of the air surrounding the capsule decreases. Conversely, the indicated airspeed decreases during a descent with a blocked pitot head. A leak in the pitot pipeline will cause the airspeed indicator to under-read. The effect of leaks in the static pipeline is normally to make the airspeed indicator overread. This is because almost inevitably the pressure surrounding the pipeline is lower than static because of aerodynamic suction. A static head is more exposed to icing conditions and is therefore more likely to become obstructed than is a static vent. A blocked static source during descent will mean that the old, higher altitude static pressure surrounding the capsule will be lower than it should be, so that if the pitot pressure is normal, the airspeed indicator will overread. This could be dangerous, in that the aircraft is nearer the stall than the airspeed indicator is showing. Note that a climb with blocked static source and normal pitot air will result in the airspeed indicator under-reading. The following checks of the airspeed indicator and pressure supply system should be made before flight. If they are fitted to your aircraft, pressure head covers and static vent plugs must be removed and stowed aboard the aircraft. The pitot tubes, holes or slots in the static heads and or static vents, should be checked to be free from obvious obstructions such as insects. Next, if one is fitted, the pitot head heater must be checked to see that it is operative. The instrument dial glass must be clean and undamaged. Finally, the instrument should indicate airspeed in the correct sense shortly after starting the takeoff run.